Welcome to Chapter 6 of Class 8 Science, Pressure, Winds, Storms, and Cyclones. In this exciting chapter, we'll explore the invisible forces that shape our weather and sometimes create dramatic natural events. We begin by observing everyday phenomena: fallen leaves swirling in the air, trees bending in strong winds, doors slamming during windy days. These are all effects of wind pressure, the force exerted by moving air. We'll understand the relationship between force and pressure, and how these simple physical principles can create powerful natural events like thunderstorms and cyclones that can dramatically affect our lives. Get ready to discover why water tanks are placed at heights, how air pressure works, and what causes those spectacular lightning shows during storms. Let's begin by understanding pressure. Pressure is defined as force per unit area. The formula is simple: pressure equals force divided by area. We experience pressure differences in everyday life without even realizing it. Remember the story of Mega and Pawan going on a picnic with identical bags. Pawan's bag with narrow straps hurt his shoulders, while Mega's bag with broad straps felt comfortable. This happens because with narrow straps, the same weight acts on a smaller area, creating higher pressure. With broad straps, the weight spreads over a larger area, creating lower pressure. This principle explains why sharp knives cut easily, why tractors have wide tires, and why camels can walk on sand without sinking. The SI unit of pressure is the Pascal, where 1 Pascal equals 1 Newton per square meter. Understanding pressure helps us design better tools, vehicles, and structures for various purposes. Now let's explore how liquids exert pressure. Have you noticed that water tanks are always placed at heights? There's important science behind this. Liquids exert pressure in all directions, not just downward. In Activity 6.1, we use two pipes of different diameters with balloons attached to demonstrate that water pressure depends on height, not total volume. Both balloons bulge equally when filled to the same height, proving that pressure depends on water column height. In Activity 6.2, we make holes around a water bottle and see water flowing out equally in all directions, showing that liquids exert pressure in all directions. This explains why dams have broader bases, to withstand the higher water pressure at the bottom. The horizontal pressure near the bottom of a dam is very large, requiring strong, wide foundations. Understanding liquid pressure helps engineers design better water systems and structures. Now let's investigate air pressure. Does the invisible air around us really exert pressure? Absolutely. The atmosphere extends many kilometers above Earth and exerts tremendous pressure on everything. In Activity 6.3, we use a paper plate and chart paper to demonstrate atmospheric pressure. When we cover the plate with unfolded chart paper, we need much more effort to lift it because air is pressing down on the larger surface area. In Activity 6.4, the rubber sucker sticks firmly to surfaces because pressing it removes air inside, creating low pressure. Atmospheric pressure outside pushes the sucker against the surface with amazing force. The atmospheric air column over a 15 cm by 15 cm area exerts force equal to gravity on a 225 kg object. We aren't crushed because the pressure inside our bodies balances the atmospheric pressure outside. Air pressure is measured in pascals, millibars, or hectopascals. Now let's understand what causes wind. Have you noticed that wind blows strongly on some days but is calm on others? Wind is simply air moving from high-pressure areas to low-pressure areas. In Activity 6.5, we connect two balloons with a straw, one inflated, one not. Air moves from the high-pressure inflated balloon to the low-pressure uninflated balloon until pressures equalize. This demonstrates the fundamental principle that air always moves from high to low pressure. This explains daily wind patterns like sea breeze and land breeze. During the day, land heats faster than water, creating low pressure over land. Air from the higher pressure sea moves inland, creating sea breeze. At night, the pattern reverses, creating land breeze. The speed of wind depends on the pressure difference. Greater difference means faster winds. Now let's explore a fascinating phenomenon. Why do high-speed winds create reduced pressure? This is explained by Bernoulli's principle, which states that when air moves faster, its pressure decreases. In Activity 6.6, we hang two balloons close together and blow air between them. Surprisingly, the balloons move toward each other. This happens because blowing creates fast-moving air between the balloons, reducing pressure there. The higher pressure on the outside pushes the balloons together. This same principle explains why roofs can blow off during storms. When high-speed wind blows over a roof, it creates low pressure above the roof. If doors and windows are closed, normal pressure inside can push the roof upward. That's why it's safer to keep windows and doors open during high-speed winds. It allows pressure to equalize, preventing roofs from blowing off. Now let's understand thunderstorms and lightning, nature's spectacular light and sound show. Thunderstorms develop when land gets heated, causing warm, moist air to rise and create low pressure. Cooler air flows in to replace it, gets heated, and rises too. This creates continuous wind circulation. Rising air cools, and moisture condenses to form clouds. Water droplets merge into heavier drops that fall as rain. But what causes lightning? Strong upward and downward winds rub water droplets and ice particles together, creating static electric charges, just like rubbing a balloon. Positive charges move up. Negative charges move down in clouds. When charge buildup becomes huge, air's insulation breaks down, and sudden charge flow creates lightning. The rapid heating of air by lightning causes expansion and the loud sound we hear is thunder. Buildings are protected by lightning conductors, metal rods that provide safe paths for charges to reach the ground. Finally, let's explore cyclones, the most powerful storm systems on Earth. Cyclones form over warm ocean waters. As ocean water heats, warm, moist air rises rapidly. Water vapor condenses into raindrops, releasing heat that causes more rising air. This creates a very low pressure area. Surrounding air rushes in, and Earth's rotation makes it spin, creating the familiar spiral pattern. The center of a cyclone is called the eye, a region of surprising calm surrounded by the most destructive winds in the eye wall. Cyclones cause destruction through strong winds, storm surges, walls of water, heavy rainfall causing floods, and saltwater contamination. The India Meteorological Department constantly monitors cyclones using satellites, helping predict their paths and save lives. Understanding cyclones helps us prepare better and stay safe during these powerful natural events. As we conclude this chapter, let's review the key concepts and their importance for safety. We've learned that pressure is force per unit area, explaining why broad straps are more comfortable and why sharp objects penetrate easily. We've discovered that liquids exert pressure in all directions, increasing with depth. We've understood that air exerts tremendous atmospheric pressure that balances with our body's internal pressure. We've explored how wind forms from pressure differences and how high-speed winds create reduced pressure. We've uncovered the science behind thunderstorms and lightning, and learned how cyclones develop over warm oceans. Most importantly, We've learned safety measures for different weather emergencies. This knowledge doesn't just help us understand our world better, it can literally save lives during severe weather events. Remember to stay updated with weather reports and always prioritize safety during storms.